Thanks for the invitation. So everything I'm going to talk about is joint work with Roland Biddleston. So we have a couple of papers hopefully coming out this fall about not the contribution of instantons to soft-dual gauge theory. So I'm going to start by reminding you guys a little bit about what soft-dual gauge theory is. It's very simple. Soft-dual gauge theory is a theory where we introduce a Lagrange multiplier field B. Can you see my mouse if I move it around? Yes.
Yes.
Yes, okay. We introduce a Lagrange multiplier field B, which is an anti-soft-dual 2 form. And we have this Lagrangian B wedge F, where F is the field strength of a gauge field. So B enforces, varying B enforces the self-duality equations for A. There's two reasons this is interesting. One is that self-dual gauge theory can be deformed by adding on this term, G squared trace B wedge B. And if we add on this term and integrate out B, we find the ordinary Yang-Mills action. Well, up to a theta angle, which is a little subtle, and we'll discuss in a minute. The fact that full Yang-Mills is a deformation of the self-dual sector has lots of interesting consequences, because the self-dual sector, at least at tree level, is integrable. And this structure, for instance, explains the very simple structure of the Park-Taylor formula for tree-level scattering amplitudes. Oops. So I actually prepared these slides for a celestial holography workshop, so some things I might not be so relevant with this talk. So perturbatively, self-dual Yang-Mills is scale invariant. Maybe let's go back to the previous slide and see why. If one looks at the Feynman diagrams, one-loop Feynman diagrams have as external fields only the A field. So the only counter terms that can appear at one loop, or higher loops, because the perturbation theory stops at one loop, are terms involving A. And the only gauge invariant quantity we can build is trace FA squared. And that's a total derivative. So in perturbation theory, it doesn't contribute. There is, of course, the possibility that non-perturbatively it is not scale invariant. And this is indeed true. So the goal of this talk is to understand the failure of scale invariance for the non-perturbative theory. So to understand this, let's look at the theta angle. So let's write down the Lagrangian again, but this time I'll include the theta angle, I'll call it theta self-dual, next to the topological term trace F wedge F. And I've included the term trace B squared, which deforms us away from the self-dual sector. Now, if we integrate out B, but at this time, take care to account for the topological terms, we find the usual Yang-Mills action here with a theta angle, but the theta angle is not the one we started with. It's a sum of the one we started with 1 over G Yang-Mills squared. So what this tells us is that the theta angle of the self-dual theory is usual QCD theta angle plus this factor, A pi squared over G Yang-Mills squared. So the self-dual theta angle is essentially the holomorphic gauge coupling. Now, there's a nice paper from Andrei Losev who computed using Feynman diagrams that the self-dual theta angle flows, and the flow is proportional to the usual beta function coefficient. So for the first part of this talk, I want to redo this calculation, but avoiding any Feynman diagrams, and instead we're going to use the Grothendieck-Riemann-Roch formula. So, but before we do that, I want to explain why you would expect that the self-dual theta angle flows with the usual beta function coefficient. So we have this identity relating the self-dual theta angle and the QCD theta angle, but the QCD theta angle is switched by parity conjugation. So at least, to leading order, it can't flow. However, the Yang-Mills coupling does, of course, flow, and it flows by this expression. So the self-dual theta angle is written as a sum of something which doesn't flow plus something whose flow we understand. Therefore, the self-dual theta angle flows by this in this very simple way. Its derivative with respect to the log of the scale is just the standard beta function coefficient. 11 over 3 nc minus 2 over 3 nf plus 1 over 6 ns. Well, these are the numbers of the rank of the gauge group, the numbers of fundamental fermions, and the number of complex scalars. Okay, so any questions so far? Okay.
Yeah, maybe I have a question. Can you hear me?
Yeah.
Okay, sounds good. So I wonder if there's any non-trivial aspect of that calculation you mentioned in this low CF paper. Because it seems like from the interpretation of this slide, I mean, it's just like standard story, right? So,
Well, I mean, no, his calculation is really, it's not the same calculation really, because he's studying the flow of the theta angle and the self-dual theory. If we go back a little bit, there's something else you can do. You can take the self-dual theory and you could forget about the topological term, but look at this trace b squared vertex as a deformation, and you can study how the beta function in the presence of this vertex. That you can also do, but that is much more close to the standard theory. We're using something. This argument in this page involves something a little subtle, which is this parity conservation statement that to leading order the QCD theta angle can't flow. Right. And this is slightly subtle because the self-dual Yang-Mills is very far from being invariant under parity conjugation. Okay. Any other questions?
Can,
Yeah.
can I add something to that question? So does it matter if you are doing the computation in perturbative vacuum versus instanton background?
Yeah, so the way I'm going to do the computation today is we're only going to see the beta function by its effect on the measure on instanton moduli space. It's like if you look at this equation here, I think it might be on the next slide. Yeah, here we go. It's on the next slide. Instantons are weighted by exactly this expression. It's e to the I theta self-dual. So from the perspective of the self-dual theory, that's obvious because the only term that is in the action that is non-zero in the instanton background is the topological term. Whereas if we were to work in ordinary Yang-Mills, the action on an instanton background is a combination of 1 over g squared plus the theta angle, and it's exactly the combination that gives me the self-dual theta angle. So this statement that the self-dual theta angle flows tells us that instantons are counted by a factor which depends on the scale in this way. Now, this is if you go read the 90s literature about the one loop measure on instanton moduli space, this is a standard. So the content of the first part of the talk is like, we want to derive this standard thing that the one loop measure on instanton moduli space flows in this way. But instead of using Feynman diagrams, we're going to use the Grothendieck-Riemann-Roch formula. So I like this because it's very simple. It's something that, all of the ingredients for this were available a long time ago and are entirely in algebraic geometry. So you don't need to know any physics. You can just use algebraic geometry and you can calculate the one-loop beta function. Okay, and any other questions? Are we good?
How is this formula proved? I mean, I don't know. I just feel like, for example, when there's the Fujikawa derivation of this anomaly. Well, sorry, maybe I should say like eventually the evaluation of the path integral becomes some determinant of differential operators, right? Even in that sense, you don't have to do Feynman diagram calculations. You just calculate the determinants.
I mean, if you want to say a determinant isn't a Feynman diagram, that's fine. I mean, of course it is, but it's a matter of. I mean, yes, this measures the measure on instanton moduli space is a determinant of the covariant derivative. So like,
Okay. How is this formula you're gonna use derive? It's not using determinant of differential operators, or
no. I'll explain. I think you'll see as we go. Yeah.
Okay.
Okay. So the way we're going to do this is I want to use the Penrose transform because I want to use algebraic geometry. So there's a really beautiful fact due to Ward that solutions of the Self-Julian-Mills equation are the same as holomorphic bundles in Twistor space. There is a Lagrangian version of this, which tells me that the Self-Julian-Mills theory is the same as a holomorphic theory in Twistor space called holomorphic BF theory, where the action is trace BFA, where A is a 0-1 form in Twistor space and B is a 3-1 form. So for this particular computation, I've written down what Twistor space here is. Here it's an open subset of CP3, but the details are not super important if you haven't seen this before. So on Twistor space, the equations of motion of this BF theory tell us that my field A, which is a 0-1 form in Twistor space, defines a holomorphic bundle. So the Ward correspondence tells us that the moduli of holomorphic bundles in Twistor space, which has a technical condition here that they're trivial on each CP1 fiber, it's not very important, is the same as this moduli space of instantons on R4. Now, Twistor space, it's a bundle over CP1 of fibers O1 squared. And there's a C star action which scales these fibers. And this C star action comes from the scaling of the coordinates on OR4. So what the RT flow is then a measure of the failure of the theory to be scale invariant. So it's an anomaly. So we're gonna compute this by the Riemann-Roch formula, which was later renamed or generalized into the family index theorem. And of course, as Hao mentioned, the family index theorem appears in the Fujikawa method of studying anomalies. So you can interpret what we're doing as applying the Fujikawa method to this anomaly, but I think it's really, we don't have to really think of determinants of operators. The way I want to think about it is the determinant line bundle has a first Chern class, or the determinant line bundle has an equivariant first Chern class, and we're computing it by the Riemann-Roch formula. So here's what the Grothendieck-Riemann-Roch formula tells us. is that there's a determinant line bundle on this moduli of instantons, and its first Chern class is given by an integral over Twistor space, the Todd class times the Chern character of some bundle, where the bundle V is a sum of various contributions from the field content. There's something from the gauge field, something from the fermions, and something from the scalars. So we're going to be interested in the anomaly for the C star action. So we want to figure out the weight of the C star action on the determinant line, which of course is equivalent to calculating the equivariant first Chern class. So the formula for this, which again we can derive by a small generalization of the GOR formula, is that the equivariant first Chern class is again the integral of the equivariant Todd class times the equivariant Chern character. And the term we're interested in is the coefficient of the equivariant parameter u. Okay, so now we can go and compute this, and it's kind of fun. We can go.
Kevin,
So
before you do that, how did you get this equivariant version of Grothendieck-Riemann-Roch from Grothendieck-Riemann-Roch?
Sure, take any variety which maps to BC star. And so like CPN. So Twistor space has a C star action, so it lives over BC star, and I can pull it back via the map from CPN to BC star to get a family of things over CPN. Now I push forward, and the determinant line is some line bundle in CPN. So it's like a standard thing to go between equivariant and families in the index theory literature.
Is the 8 here also just 6 plus 2, where the 2 comes from C star?
It's because I'm looking at the first Chern class. Twistor space is of real dimension 6, and the first Chern class is of degree 2, so I have to integrate out Twistor space that subtracts 6 of the cohomological degree. Okay, thanks for the questions. I have a tendency to go way too fast unless people slow me down, because I assume it's all obvious. Okay, so now once we've gotten to this formula, it's really fun to plug in the Todd class, which is built from Bernoulli numbers, and do some manipulations and find the 11/3 number of colors and so on popping out. So let's do this. If you plug in that, if you look at the formula for the Todd class, and you compute what it does to the tangent bundle of Twistor space, you find it looks like this expression where H is the hyperplane class. So notice that there's an 11/6 appearing, which is promising because we wanted to get an 11/3 in the end. Now the matter fields, it's like the bundle on Twistor space, which encodes our gauge fields and our fermions and our scalars, is written here. It's a sum of a bunch of things. For the gauge fields, there's the adjoint bundle and the adjoint bundle tensor K. For fermions, there's fundamental plus anti-fundamental, and then there's powers of K to the quarter and K to the 3/4. And for scalars, we get K to the half. Next, the equivariant Chern character of the canonical bundle to some power is given by this expression, e to the minus 4AH minus 2AU. So this calculation is more fun to do than it is to read, really. So then we see that, the Chern character of our bundle, it's some polynomial in U and H. We multiply by the Todd class. And we get, here's the important thing is here at the end. we get some number, and the number is the one we want, minus 11 over 3 NC, 2 over 3 NF, 1 over 6 NS, but it's multiplied by the second Chern character of E. That's the instanton number. So that's good. So the beta function coefficient is going to multiply the instanton number exactly as we expected. And it's also multiplied by U, which is the equivariant parameter, and one copy of the hyperplane class on Twistor space. And we need that copy of the hyperplane class so that the hyperplane class times the second Chern character together give you a volume form in Twistor space. So when we integrate this over Twistor space, we get the instanton number times the equivariant parameter times the beta function coefficient. Okay. Hi, Simon?
Hey Kevin, sorry, quick question. Can you maybe explain, is there any intuition why this 11 over 6 appears in the Todd class? I mean, maybe that's...
Oh, so what's the formula for the Todd class? It's like the Todd class of a line bundle is, it's x over 1 minus e to the 1 minus e to the minus x. So there are Bernoulli numbers appearing. So there's like a half and a 1 over 12. You just fiddle around. I mean, the Twistor space is an open subset of CP3, and I need to compute the Todd class of the tangent bundle of CP3. You use the Euler sequence, which expresses the tangent bundle of CP3 in terms of 4 copies of O1 and 1 copy of O, and there's just some little manipulations.
I see. Okay, thanks.
No great insight. Yeah.
I have 2 questions.
Mhm.
One of them is that at the beginning you mentioned the classical theory was integrable.
Yes.
Is this computation you are doing implies a breakdown of that integrability? It's first question. And the second question is related to my former question. Now, this answer is proportional to instanton charge. If you were to do this in 0 instanton background, you would get 0.
That's right.
So does it mean that in the perturbative vacuum, there is no running in this BF theory?
That's correct. So let me answer the second question first. Self-dual gauge theory and perturbation theory is scale invariant. It's a CFT. Because the only counter term that appears is trace f squared, and that's topological and invisible in perturbation theory. That makes sense?
Yes, of
Yes.
course.
Yes. So for the first question, the theory does fail to be integrable at loop level, but the failure, there's a slightly different index theory computation that tells us about that.
Okay.
So which I don't think I'm really, well, I'll say a little bit about that at the end.
Okay, sounds
Okay.
good.
Any other questions?
I also have a question. So this computation, it seems that it doesn't really need to use like a normal anomaly cancellation conditions for the theorem Twistor space.
Yes.
Yeah, so it's it seems that it's deriving some correct result from something that suppose doesn't make sense, right?
I think what's going on is the theory on Twistor space. It has one loop anomalies, some of which are equivariant and some are non-equivariant. So if I was to compute the full anomaly, you would find the coefficient of U is the beta function coefficient, and the term without U is the anomaly you're mentioning. So I feel, yeah, I think they're just independent. Like yeah, I think these two things can be treated separately.
Okay.
I do see where you're coming from, but So that was just an introduction in some ways, because I mean, I wanted to explain this because I think it's really fun to compute the beta function coefficient this way. It's a nice way to see where all these numbers come from. And if I was teaching a course to mathematicians about why Yang-Mills theory is asymptotically free, I would definitely do it this way. But I also want to explain another way to think about it, which comes from the topological string. And this part of the story is really a small part of a much bigger project, which I honestly haven't made a great deal of progress on, and other people are looking at aspects of it. So this starts by noting that there's a connection between self-dual gauge theory and the topological string. So this originally appeared in the Twistor string theory of Witten and Berkowitz. They said that self-dual n equals 4 comes from placing topological B-branes wrapping CP3/4. The CP3/4 is a Calabi-Yau supermanifold, and it's like a super version of Twistor space. So I want to generalize this to discuss theories with less supersymmetry. So before we do that, I want to explain an alternative and very simple way to think about what Witten and Berkowitz did. So all mathematicians know that the B model on an odd vector space V is the same thing as the B model on an even vector space, V dual. And this is just causal duality. Branes in the B model on the odd vector space are modules over the exterior algebra, and on the even vector space are modules over the symmetric algebra, and causal duality gives an equivalence between them, as long as we take some care about completions. Now, we can do this not just to vector spaces, but to vector bundles as well. And it tells us that the B model on CP3/4 is equivalent to a purely bosonic B model on this Calabi-Yau sevenfold, O1 to the 4th over CP3. From this perspective, n equals 4 super Yang-Mills, it's no longer a space-filling brane. It's a brane which wraps the 0 section inside of O1 to the 4th. So what we would like to do is, can we study holography for self-dual n equals 4 by using this topological string relation? From the perspective of holography, this topological string realization is better because the back reaction is going to involve removing the support of this CP3 brane. Now, if I had turned my bosonic fields into fermionic fields, that wouldn't have made sense. So it's really essential that we work in this bosonic frame if we want to talk about holography. But I also want to do similar things for theories with less supersymmetry. So I will want to generalize this construction. So here's the generalization. So we take an even-dimensional Calabi-Yau, which has a C-star action, where the volume form is weight 4. And then we can build a Calabi-Yau, which is the total space of a Z bundle over Twistor space, where we twist Z by the line bundle O1. Because the canonical bundle of Twistor space is O-4, because it's a subset of CP3, this will be a Calabi-Yau manifold. So the -4 from Twistor space and the 4 from the fibers will cancel. And an equivariant sheaf on Z will give rise to a sheaf on this Twistor space. And then we can try to play holographic games by back-reacting this brane on Twistor space. So here are some examples. I take Z to be C4, with all weights being 1, then we get n equals 4 super Yang-Mills. If I take z to be C2, the weights 1, 3, then we get n equals 1 self-Joule Yang-Mills, again, like the Twistor realizations. If I take z to be C2 times C2 mod gamma, where gamma is a subgroup of SU2, then we can engineer the Twistor realizations of n equals 2 affine quiver gauge theories. This is kind of essentially a standard string theory construction. And we can also get examples which have no supersymmetry by taking z to be T star of CP1. Of course, it's a resolution of C2 mod Z2. With a certain C star action of weight 4 on the fibers and weight 1 on the CP1. And I want to build a sheaf which is a sum of the structure sheaf of CP1 with a parity conjugate, parity shifted version of O minus 1. And here this means C lower 2 means the C star action has been changed. It's not so important. This example gives you a non-supersymmetric theory, UN times UN gauge theory with bifundamental fermions. Okay, so in this way, starting with a Calabi-Yau manifold with a C star action, we can build a Twistor space and engineer self-Joule gauge theories by thinking about topological strings on that Twistor space, generalizing the Witten-Berkovitz construction. Okay, any questions about this?
Oh, sorry, maybe I have a quick question. Do you know like what I mean, there's obviously like a lot of generalizations of this one could ask about. Like, I mean, I don't know, say what would happen in the last example if you somehow scale I don't know, like distribute the weight between scaling on the CP1 and the tangent directions, or have something like weight 5 and weight -1 or something like this?
Well, the cotangent fibers always have to have weight 4 because the symplectic form is invariant under rotations of the base, but scales under the scaling of the fibers. But you can give different weights to the base, and that just you end up with various things that fields of weird spin. So I chose these examples to get fields of a reasonable spin.
Thanks. Okay.
Well, so as Key mentioned, these theories on Twistor space are sometimes anomalous. So there's two kinds of anomalies. There's the usual chiral anomaly that we see in spacetime, but that's actually not going to appear in any example we're considering. The anomalies that are important to us are anomalies which prevent integrability. So these anomalies are related to the one-loop all-plus scattering amplitude on spacetime. The point is, any theory, four-dimensional theory, which at loop level, it comes from Twistor space, must have vanishing scattering amplitudes. So this anomaly is proportional to the trace of x to the fourth, where x is a matrix, and the adjoint minus the matter. So we might wonder how we see this from the topological string. So the standard story in string theory, and also in the topological string, is that the theory on a brane is anomalous if there's something which prevents us from finding the field sourced by the brane. In other words, the theory will be anomalous if the charge of the brane is not zero in cohomology, because the field sourced by the brane is something which d bar of which is the charge of the brane. Now, the cohomology of Twistor space is just the equivariant cohomology of z modulo q squared of this, z version of Twistor space. So the charge of the brane is just the equivariant Chern character of my sheaf, modulo q squared. Actually, previously, for some reason, I used the word u for equivariant parameter. Now I'm using q. So sometimes on space-time, we find that anomalies are cancelled by the introduction, like these Twistor anomalies are cancelled by the introduction of a fourth order scalar. So this is a kind of a Green-Schwarz mechanism. So on Twistor space, this is literally a Green-Schwarz mechanism, and the theories we're considering sometimes include these fourth order scalar fields. But they're built into the formalism. They just pop out of the string theory construction in a way which I hope is familiar to people. For example, let's take Z to be the cotangent bundle of CP1. Then we're building a Calabi-Yau fivefold, which fibers over Twistor space, and the fibers are the cotangent bundle of CP1. Sometimes there are closed string modes which are trapped on that CP1, and they can't be decoupled when I try to build the open string field theory. So this should be familiar to people who study type 2b, the way the 2-0 theory arises by compactifying type 2b theory on an orbifold. It's in fact literally the same mechanism. So what we find is, if I have a sheaf on Z such that the equivariant Chern character vanishes modulo q squared, then I can build a consistent topological string theory and an anomaly-free theory on Twistor space. But sometimes, depending on the geometry, we have to include these axion fields. Okay, I think I went through that a little fast. Okay, any more questions? Okay. So let's look at this example. If Z is the cotangent bundle of CP1, then the theory we get on spacetime is UN times UN self-G Lang-Mills with bifundamental fermions. If you recall, the formula for the anomaly was like trace of x to the fourth and the adjoint minus the matter, and you compute it, you find that there's a double trace anomaly, which is trace in one copy of UN squared times trace in the other copy of UN squared. Similarly, on spacetime, there's a double trace all plus amplitude. But this example, it has a compact CP1, which is associated to a closed string mode, and that introduces an axion field which precisely cancels this anomaly. The axion field is a scalar in spacetime and comes from the Riemann-Roch form integrated over a 4-cycle, which is a CP1 in Z and a CP1 in Twistor space. And if you like, the topological string we're talking about in this Calabi-Yau fivefold is really a subsector of type 2b. So this axion field is related to the 1,0 tensor multiplier. Okay, so the program is, can we study holographic duals of self-dual gauge theories without supersymmetry by using this topological string realization of them? So the dream would be, had to have exact holographic duals of theories which are not supersymmetric, but are simple in a different way in that they're self-dual. Now, it's very nice to dream this, but there are some immediate difficulties. The first difficulty is local operators in the 4D gauge theory are non-local on Twistor space. On Twistor space, they might be determinant operators. Therefore, whatever is dual to a local operator in 4 dimensions, it's not just going to be a graviton in the usual sense, it'll be something much more complicated. So I'm not going to address that difficulty today. I'm going to address another one, which is that the theories we're discussing, they flow, the theta angle flows. So we would, as a first step to understanding this putative duality, we want to see the flow of the theta angle as something happening in the back reactor geometry. Okay, questions? Okay. So we can ask what quantity in the back-reacted geometry could possibly be flowing. And so we have to figure out what quantity corresponds to instantons. Well, instantons are holomorphic curves in Twistor space. So they're D1 branes. So whatever must correspond to the theta angle is a field that couples to D1 branes, and that will be the Riemann-Roch form. So what we need to do is calculate how the Riemann-Roch form flows in the back-reacted geometry. So let's first understand what possible Riemann-Roch forms there are. So let's look at, we have Z, which is our Calabi-Yau. Could probably focus on Z being T star CP1. Then I can remove the exceptional locus, which might be CP1. And I get a fibration, again, over Twistor space where I've removed some exceptional locus. It turns out that the back-reacted geometry is just this geometry, but with some fluxes turned on. The fluxes are certain cohomology classes. And the cohomology of this geometry, well, there's a class in H3, and there's a class in H2. Class in H2 is, of course, the class in H2 of Twistor space, corresponding to a CP1 in Twistor space. The class in H3, if Z, we're assuming Z is of complex dimension 2, the class in H3 comes from the fact that there's a 3-sphere wrapping the exceptional locus that we've removed. Now, the class in H3 corresponds to the field strength of Riemann-Roch form, and this has to be n, if I have branes of charge n. Whereas the class in H2, this corresponds to Riemann-Roch forms which have vanishing field strength. In other words, they're flat gerbs. So here's the computation. So remember, we have a brane given by some sheaf F. The anomaly vanishes if the Chern character is 0 mod q squared. If this is true, then we can build the back-reacted geometry. And the next coefficient of the equivariant Chern character tells us how the Riemann-Roch form flows. So to be more precise, if I want to think about an instanton given by a D1 brane, and I want to think about the one-loop measure on instanton moduli space. The instanton is also given by some sheaf on Twistor space, built from some equivariant sheaf on Z. And the one-loop measure can be thought of as a closed string, which on one end lands on the brane F, and the other end lands on the instanton. So the computation is that the failure of the one-loop measure to be scale invariant is given by the Mackay pairing of this coefficient of the equivariant Chern character of F with that of G. So really what we're doing is we're thinking about the one-loop determinant by viewing this annulus amplitude as an exchange of closed strings instead of as viewing it as an open string, as one would normally do. Okay, I think this. So how do we prove this? This is just an explicit, a completely explicit computation. We take my Z, and I build my Twistor space whose fibers are Z, and I try to compute in coordinates the field sourced by the brane. And something funny happens when you try to patch these things together, and that funny thing involves a logarithm, so that the field sourced by the brane on the global geometry fails to be scale invariant. So here's a simple example. If Z is C2, the weights 1, 3. I hope you haven't forgotten that this engineers n=1 gauge theory, and n=1 gauge theory is a beta function. The beta function is 3nc. Now I take my sheaf to be Cn, and we would like to see 3nc appearing. How do we see that? What's the equivariant Chern character? It's n times 1 minus e to the minus q, and 1 minus e to the minus 3q for the weights, and indeed this gives us the correct answer. For n=4 Yang-Mills, it's conformal, and of course we see that too. And for all the theories we've discussed, this gives us the correct beta function. Okay. So I think this is the end of the talk. So what I've presented is two ways to understand the beta function of self-Joule Yang-Mills by thinking about one by the Grothendieck-Riemann-Roch formula and the other by the index theorem. By thinking about the topological spring. Now, so for me, the interesting part about the second is that it's really the beginning of a much broader program to understand self-Joule theories holographically. So it's a very preliminary check that the most basic aspect of these theories, namely the fact that they have a non-trivial beta function, can be seen in the back reacted geometry. Okay, so I'll stop there.
Okay, let's thank the speaker. Do we have any question?
I have a question.
Mm-hmm.
Maybe multiple question, but one thing that you brought up, and that's quite interesting, is that, for example, if we start with pure Yang-Mills and make a restriction such that PET integral localizes to self-dual sector, so we obtain this self-dual theory that you described. So now in this new theory, there are instantons, but no anti-instantons, right?
That's correct, yes.
Yeah. So I think that this theory does not confine.
Good question. I mean, you can view this theory as a limit where G Yang-Mills goes to 0 while keeping 1/g² plus I theta fixed. So I don't know if this confines or not. I know what will be your argument for why it doesn't confine?
So the instantons wouldn't interact with themselves. They are all BPS, right? It's a very interesting statistical mechanical system because you have objects, but their mutual interaction is 0.
I wouldn't say the mutual interaction is 0, right? It's not like, you can get an instanton as generated from an instanton of some subgroup, but the instantons from those two subgroups do interact with each other.
No. If they are both self-dual, the interaction is identically 0. It is, if you look to ADHM data, there is multi-instanton solution, instantons with charge K, and their moduli is 8K n-dimensional.
Yes, but when they're far apart, they separate into separate instantons.
Yeah.
When they're close together, they merge. And so I thought of that. Okay.
And there are more reliable sources. I know the answer to my question. If I consider these theories, for example, take n=1 super Yang-Mills theory you mentioned.
Mm-hmm.
If I compactify it on R3 cross S1, okay, with periodic boundary condition for fermions, then if I construct the counterpart of your VF theory, there are only monopoles, but no anti-monopoles.
Yes.
Monopoles have 2-0 modes, but now they will not be able to generate a bosonic potential, which ultimately leads to, mass gap and Polyakov-like confinement. And
Mhm.
in that, at least on R3 times S1, one can rigorously prove that the theory does not confine, it doesn't have a mass gap.
Okay. I wasn't aware of that.
Yeah, with this restriction, yeah.
Good. What's a good reference for that? Is there?
I mean, there is no good reference. I'm thinking about it, but there is reference
Okay.
for the confinement on R3 cross S1. What happens is that, for example, if you take n equal 1 super Yang-Mills theory, there are
Mhm.
monopoles and anti-monopoles. Of course, monopoles leads to superpotential, and you evaluate bosonic potential by taking derivative of the superpotential. You can reinterpret the bosonic potential in terms of pairs of monopoles. You know, for example, monopole associated with some root alpha I and anti-monopole associated with root minus alpha I plus 1, things like that. Those objects leads to both mass gap and linear confinement. You can show that part. But now you are taking away half of the story. You
Yeah.
are removing the anti-monopoles, and I would think that at least in that context, it wouldn't confine this BF theory, which is very interesting because if it is true, I mean, then it shows some necessity condition, right? That the existence of these. Okay.
Yeah.
I have other questions to ask, but I will stop for the sake of other people who wants to ask questions. Then I will ask later, maybe.
Yeah. Thank you. Mhm.
I was
Okay, do
wondering
we
if
have
you can get the Friedan beta function for the Ricci flow by using some similar techniques. So the beta function for 2D sigma models.
Yeah, I'm actually writing something with Davide about that, where you embed 4D transaminds in the topological string, and what you derive is like there's a formula. You got these 2D models engineered from Riemann surfaces with the one
Mhm.
form, and then there's kind of conjectural formula for the flow in terms of the periods of the one form. So you can derive that from the holographic dual.
I see. Thanks.
Yeah. Mm-hmm.
any other question? Okay, I have one. So is there any particular reason you consider you start from this string construction from equals 4? This bird.
Oh, I just thought people would be familiar with the Witten-Berkovitz story. That's all.
Okay.
In many ways, it's a weird example because Calabi fivefolds are kind of better than Calabi sevenfolds. So
Okay, I have one more question. So
Mhm.
perturbatively, it is easy to see that this B square term is not generated.
Yes.
Because the corresponding diagram is 0. But is there a symmetry reason for that?
Yeah, I mean the action has if I scale B in the action, then if I introduce something called like H bar in front of the action, then the action is invariant under simultaneously scaling B and H bar. So that means that one loop diagrams can't have any B's in them because they come with the coefficient of H bar to the 0. So this tells us that even in the presence of instantons, you can't introduce this term.
I see. So you are treating H bar as Spurion field, something like that.
Oh, it's just some parameter which measures a loop number, that's all.
Oh, okay. Okay.
Sorry, maybe I have another quick question as well. So, I mean, I guess in previous papers, you often considered like just the anomaly cancellation using only the axion with some, say, like SO8 gauge group or something.
Mm-hmm.
Does this theory have a beta function, and how does this maybe fit into
Yeah, this does
the
have a
context
beta.
of what you talk about?
That theory does have a beta function, and it also has a string realization. It's just more complicated. How does- And see, so sorry, let me backtrack a little bit. If I just have a single gauge group like SO8 and it has an axion field, if I have this beta function, actually this determinant on instanton moduli space, which flows when I scale, because I also have an e to the rho, I'm multiplying because the rho f wedge f term. See, if my theta angle flows, you can absorb it into a shift of rho. So in a theory like that, what you're finding is not that there's a beta function, but that the field rho has some dimension. The dimension being the beta coefficient beta 0. So which is an interesting thing, right? It gives you some constraint about the 2-point function of that. It's a little bit like, I don't know, like Liouville theory or something like that.
Have we learned something about confinement using your holographic framework?
If I knew something about confinement, I would be trumpeting very loudly, but of course I don't. So I mean, the issue is, you know, the thing you want to see is you want to see the area law for Wilson lines. And ordinary Wilson lines are kind of tricky to see in Twistor space. The thing you can try to think about is null polygonal Wilson lines, and they are related to branes. But yeah, I haven't been able to say anything about them. I think there's a project with like David Skinner and Atul Sharma are like, I think, studying this kind of the brane realization of null polygonal Wilson lines.
I have one more question, but it may be a little bit naive. So if you excuse me, I will ask.
No. I'm a naive person, that's all.
Okay. So if I have self-dual fields, and if I look to their stress energy tensor, at the classical level, they all vanish. In particular, you know, for 4 component, which is the energy, they vanish. And this is regardless of, I look at this tensor either in Minkowski space or, you know, Euclidean space. It doesn't really matter.
No, I wouldn't. I mean, the stress energy tensor is, you know, B times F. So I wouldn't say vanishes. It's trace free.
So if I start, for example, let's say I am pure Yang-Mills theory.
Yes.
The stress energy tensor in Euclidean space for 4 components is something like minus E squared plus B squared. And self-duality imposes E is equal to B.
See, I would have said, you know, the definition of the stress energy tensor is like, I think how my theory behaves when I change the metric. And so self-dual gauge theory depends on a metric. Because the Hodge star appears. So I change that.
I
So
agree with you on that. So
I would have
in
said
the Hodge star, there is metric. But I am bringing another perspective. Let's start from pure Yang-Mills theory. For example, look to 4 component of the energy momentum tensor. It's minus E squared plus B squared. And for the instanton E is equal to B. And you can make the same statement in Minkowski space. Of course, T44 is electric field squared plus magnetic field squared. But now self-duality equation is I times E is equal to B. Hence, it is probably something like positive chirality Goulion or something like positive helicity. I'm sorry, helicity Goulion. And for both of them, it is identically 0. And this thing confuses me, honestly. I mean, how can this object, this self-dual configuration can have 0 energy and at the same time So that means they cannot transport energy, right? And at the same time, how can there be a non-vanishing beta function or RG?
I am also confused. Yeah, I would not have thought that the stress energy tensor was 0 of that. I bet it sounds trace-free, but especially if you write down the instanton solution, it depends on time explicitly. I mean, of course, it's Euclidean, but if I try to analytically continue the coordinates.
Sure. But so the energy associated, if you write the energy tensor, that is stress energy tensor associated with instanton, I think it's strictly 0. I mean,
I'm not sure what you mean. You mean like the expectation value of the stress energy tensor in an instanton background, or
no, as a classical.
I'm confused because it's not a number; it's an operator. So I don't think.
No, as a classical configuration.
No, you
I'm
just
evaluating-
evaluate. I
I'm
see what you're saying.
Oh.
I mean, the stress energy tensor is B times F, and the instanton I only F as a non-zero value and B as a 0 value. So of course it's 0. That must be what's going on.
Maybe it is related to that in the BF theory. I was saying it from the
Yeah.
instanton perspective, but it's okay. So, and in the Minkowski, right, I times electric field must be magnetic field. So in some sense, electric field must be purely imaginary, magnetic field must be real. But in that case, we have this component is E squared plus B squared, and it again vanishes. So it looks like if we have some, for example, if I build a plane wave, which is self-dual, right? Its energy density classically must vanish, and that confuses me a lot. But you also said that, this one loop result was a result in the instanton background and not in the perturbative vacuum. Maybe there's a catch there.
Yes. Yeah. I feel like maybe it's too difficult to understand all these details over Zoom.
Oh, okay, sorry, maybe.
Yeah, no.
Okay, if we don't have any further question, let's thank the speaker again. Thank you, Kevin.
Thanks very much, Kate.